Okay, so we're going to prove Cauchy's theorem. Cauchy's theorem is another really powerful little tool, like Lagrange's theorem, to allow us to characterize groups. What Cauchy's theorem says is you take any group G, some operation, so G with some operation dot is a group. The size of G is some number, let's call it n. And now, if there's some prime number, I mean, any n is going to have some prime factorization, so take any of the prime factors of G. So P is a prime such that n is divisible by P. And for this prime, it has to be the case that there exists an element of G. So exists some element A in our set such that A to the P is the identity. And then what follows from that is that there's a subgroup of G, so there exists some subgroup of G with such that the size of the subgroup is P. This follows from that because P is prime, and the other thing is that H is just the set generated by A. Okay, so this is Cauchy's theorem. It's very powerful because it allows us to characterize subgroups of any group just by looking at its prime factorization. So this is Cauchy's theorem. We're going to prove it, and we're going to prove it using the concepts of group actions and orbits and stabilizers. And as a quick reminder, so we're going to use the orbit stabilizer theorem, which is a very generally useful thing. The orbit stabilizer theorem says that if you have some group G acting on some group, acts on some set X, and then take any element of X, a big X called little x. So for all little x in big X, this is the orbit stabilizer theorem. It says that the size of the orbit of X times the size of the stabilizer of X equals the size of the group that's acting on X. So it's a connection between these are all elements of X, and this is G. So anyway, this is going to be the thing that we'll use in the proof. Oops. So we're going to first of all define an action involving our group G. So to prove this thing, we start with the assumptions. The assumptions here is that we have a group. This group size is n, and that there's some prime number P such that P divides n. So n is divisible by some prime P. These are our only assumptions, so whatever we say should be true for any prime that divides n. So what we're going to define is we're going to define an action. This action is going to be, so first we'll say what the set that's being acted on is. X is going to be the set of all P tuples of elements of G. So we'll say, elements G1, G2, etc. up to GP. For all, so I'll say this thing, which is an element of G to the P, and then we're looping over all such things with our constraint, with our only condition on this being that when you multiply each of these guys together, you get the group identity. Okay, so our condition here being that G1 times G2 times etc. Up to GP equals E, the identity. Okay, and this is our set X that's being acted on. It's a little unusual, but it'll end up being what works for us. Let's quickly ask, what's the size of X? So the size of X in terms of n and in terms of P. So there's P elements in each, this is a P tuple, and each of these elements, there's n possibilities for it, right? So it seems like we might say naively this thing is n to the P, but that forgets that we have this constraint here. This constraint, you can think of it as so this constraint basically removes the degree of freedom from our last element here, because you choose the first P minus 1 elements of this tuple, right, members of the tuple, and then the last one is fully constrained, because the first one, the first P minus 1 multiplied together give you some element of G, and then there's exactly one element, so let's say G1 times G2 up to G to P minus 1 equals G for some G. And then you have this times the last element, G sub P, has to be equal to E. There's only one element here that'll do that. So once you've chosen the first P minus 1 elements, you've already fully constrained the last one. So there's really n to the P minus 1, right? P choices for each of these except the last one, which is 1. So that's the size of X. That's the set that's going to be acted on. Our group is actually not going to be this group, G. What we're going to choose for our group is just the integers mod P, which is a little bit of a weird choice under addition. So it's a cyclic group, right? We previously talked about the integers being generated, integers mod P being generated by 1 under addition, because you have 1, you have 1 plus 1, which is 2, 1 plus 1 plus 1 is 3, etc. up until added to itself P times you get back to 0. This thing is going to be acting on X. So Z, P acts on X. So the way it acts on X, I'm just going to write one thing about the way it acts on X, which is going to specify all the behavior. But all we need to say is this one thing, which is that take 1. 1 is an element of integers mod P, acts on X, which we'll write as a big dot. And what it does, now let's write out an element of X, so just sum G1, G2, etc. up to GP. What it does, this is a way to generally write these elements. What this will do, let me just horizontal. What this does when you act 1 on this is it just cycles things around. So it moves GP to the front, moves the rest of them all over by 1.
Okay.
So this just becomes GP, then G1, G2, etc. up to GP minus 1. Okay. Now this fully specifies everything because the group action has to satisfy a few constraints, like a type of associativity. Compatibility is what it's called.
Okay.
And so that would tell us that act 1 on this twice, and that's the same thing as acting 2 on it, right? Acting 1 on it twice just loops this around 2 times, so you end up with G, P minus 1, GP, G1, G2, etc. up to the end. And then you can do the same thing for 3 and 4 and all the other elements of ZP. So this kind of fully specifies what our action is. Our action is basically just, cycle it around P, n times for some n. Now, so this is our action, we fully defined it. Now we're going to ask about the orbits and the stabilizers of elements. So first of all, take some element little x in our set, and we ask, okay, so this element has some orbit of x. Now what are the possible sizes of this guy, given what we know from the orbit stabilizer theorem? So we know that the orbit of x, the size of the orbit of x, times the size of the stabilizer of x, which is some other integer, some other positive number, has to be the size of the group that's acting on it. Now the group that's acting on it is ZP, right? It's not G. So the size of the group that's acting on X is P. It's the integers mod P. So this thing has to be something which you can multiply some positive number, so this is some positive number. Multiply some positive number by the size of the orbit of X, and you get back the size of ZP, which is just P, right?
Right.
Now, what that tells us is that, some integer times some other integer equals P. The only ways this will work, since P is a prime number, is that one of these is 1 and the other one's P, right?
Yeah.
So this basically what this tells us is that the size of the orbit of X is either 1 or it's P. So for, or the possible sizes of orbits are either 1 or P. Okay? So, right, so those are the possible sizes of orbits. Now, we can think about an example, like the orbits of size P kind of makes sense, because what we're doing, take a given element, and then operate 1 on it, and then you loop back around, operate 2, you loop it around twice, and it kind of makes sense. Once you've looped it around P times, you just fully looped it around, you ended up with the same element. That kind of makes sense. You have elements of size P. It's a little bit weird that we get elements of size 1, but if you think about it, an easy example of an element of big X of whose orbit is 1 is just this guy. The identity, the identity where there's P of these,
Mm-hmm.
so this is obviously a P tuple of elements from G. G has an identity, these are just P of them. They meet this condition, multiply E times E times E times E, P times, you get back E. And in addition, when you loop it around, when you bring this guy from the back up to the front and do it over and over again, you're always getting the same element. So, the set of elements you get by applying this action in all possible ways with elements in G is the orbit of this element. So clearly, you're always just getting this element back. So there's only one upside element of this orbit. So we have at least one example of an orbit of size 1.
That's nifty.
Now the question is, how many elements are there whose orbit is size 1? And how many orbits are there of size P? That's going to be the important question for us. So let's give them names. Let's say R is going to be the number of orbits of size 1. And then S is going to be the number of orbits of size P, right? Now we're going to use another fact, which is another fact about orbits, which is that orbits partition up a group, partition up our set X, right? So what that means is that if you just look at the set of all orbits, none of those two orbits will share elements. They'll all be completely distinct and disjoint from each other, and every element of our set X is going to be in some orbit, right? And that's, again, I think you can just prove by looking at the properties of group actions. What that means is that, these are all our orbits, right? We have R orbits of size 1, we have S orbits of size P, so those contain all our elements. So we can add up all these elements, the size of X has to then be that sum.
Right.
So there's R orbits of size 1, so there's R orbits with one element in them, and there's S orbits with P elements in them. These are all unique elements because the orbit, because it's a partition. So R plus S times P is the size of X.
Good.
We already figured out the size of X. It was n to the P minus 1, right? Okay. So n to the P minus 1. Now we're going to use our other assumption, which was n is divisible by our prime number P, right? That means, n is divisible. So, okay, if n is divisible by P, then n to any power is also divisible by P, any positive power, right? Because then you're just multiplying n by itself a bunch of times. The prime factor stays in there, it just gets multiplied just as well. So n is divisible by P, which means this thing is divisible by P, which means this thing has to be divisible by P.
Right.
Now that gives us a constraint on the possible values of R and S.
Right.
Right? Now, what is that constraint?
Also?
Yes. Not on S.
Cool.
Because it's a constraint on R. What is that constraint? Well, this thing has to be divisible by P. It's a sum of two things. This side is clearly divisible by P. It's just a number times P.
Yeah.
So if we have something plus something has to be divisible by P, and the second something is divisible by P, the first thing also has to be divisible by P. So this tells us that R is divisible by P.
That's so cool.
Right? Now, there are a bunch of choices of things that are divisible by P. One of them is actually 0. 0 is divisible by P.
Oh.
Right? 0 divided by P is an integer.
Okay.
So 0 is a choice. Is 0 a possible value of R? Well, we already know there's at least one element whose orbit is size 1. R is a number of orbits, so we know R is greater than 0. So it's not 0.
Okay.
But the other choices are that R could be P. There could be P orbits of size 1. There could be 2P, 3P, etc. But importantly, the only fact we need is that R does not equal 1. No matter what P is, for any prime, 1 is not divisible by that prime. Right? You always get 1 over P, which is a fraction. So R is not 1, which means we found one element whose orbit was size 1. We found one orbit of size 1, which is identity element. There has to be at least one other element in here, right?
Right.
So let's think about what that element looks like. I'll do it over here. So we have some element. It has to follow the same property that it just, some element of G, A, let's call it, P times, this should be parenthesis. It has to be that way because otherwise the orbit wouldn't be size 1, right? The orbit here is size 1 because every time you bring this to the front, you get the same element back. If some of these were not A, then you would actually get something different when you cycled through, and you'd have an orbit larger than 1.
Mm-hmm.
So the form of this element is constrained by the fact that its size is 1.
Mm-hmm.
And in addition, A does not equal E, because we know there's more than just that one element. We can choose, there's at least one other element A, such that this thing is an element of our, is an element of X.
Mm-hmm.
And using our constraint up here, we know that A times A times A, etc., up to P times, in other words, A to the P, has to be the identity. In other words, there exists an element of G, A, such that A to the P is the identity.
That's really
And that's
cool.
the proof. And it's super clever and weird. Like, you have to be, I don't know who thought up using this specific set and this specific group.
Maybe it was Cauchy.
I don't know, yeah, I wonder if this is the way he proved it or if it was someone else.
That's so cool.
But yeah, so this is the proof of Cauchy's theorem.